Good afternoon. Good afternoon, everyone, and welcome to this EMOS webinar. My name is Caterina Giusti. I'm Professor of Statistics at the University of Pisa in Italy, where this session is hosted. And today I will also act as the webinar facilitator. So now let me first explain for any newcomers that EMOS stands for the European Master in Official Statistics, a joint project of universities and data producers in the EU member states, EFTA, and EU candidate countries. If your university is interested in applying for the EMOS label, please consider that the permanently open call for universities is available on the EMOS dedicated page on the Eurostat website. For staying in contact with the EMOS news and community, please follow the EMOS Twitter. The EMOS account is @EU_EMOS. It's now time to start with our webinar. Before I give the floor to our speaker, let me first display how we run the webinar today. As for the previous webinar, the EMOS webinar stream on the EMOS YouTube channel, where you can already find the recording of the past webinars. As a participant, you can watch and listen to the webinar. To use the chat to interact with the presenter, you need to log in YouTube using a Google account. We encourage you to prepare your question, post them to the presenter during the presentation or the final discussion. Should you have any technical problem, you can contact us at the email address that is indicated in the chat. So today I have the great pleasure to host Jo Røislien. Jo is a research scientist, communicator, and author. He is professor of medical statistics at the University of Stavanger and have been involved in numerous research projects in medicine and health. He has also been in front of and behind the camera on several science TV series, also for Discovery Channel. And today, Jo will present about statistics, more than numbers. So, Jo, now the floor is yours. Thank you for joining this webinar program.
Thank you so much. Yeah, statistics. I mean, I love numbers, and talking about numbers is something that I really cherish. But it is important to remember that for me, being a statistics professor was actually my plan B. My plan A was to become a pop star. And obviously didn't turn out that well, since I ended up a professor in statistics. You know, everyone who's a struggling artist needs a side gig. So while most people who want to be artists work in bars or restaurants, I did a PhD in probability theory. It was more freedom. I could come and go as I wanted. And when my whole artist career didn't happen, I fell back to numbers, which means that my interest is not in pure mathematics and pure numbers, but what numbers can do for society and how we are all dependent on numbers, and how numbers is something more than just quantities that we put on something, but it has a bigger effect. And I started out my career as a mathematician. I was a tiny little nerd. I thought I was going to be a mathematician. I loved maths in school. I aced all the tests, and then I started studying mathematics at university. And to me, mathematics, it was a little bit too pure. It was too beautiful. It was too compact. And I like stuff that's dirty, that's hard to comprehend, hard to sort of untangle. So I drifted from pure mathematics and over to probability theory and statistics and numbers. And all my career sort of started in a very pure sense, doing mathematics. And there, numbers, I mean, they're really clear cut. In mathematics, you know what 2 means. You know what 2 + 7 is. But when you start using numbers in engineering and natural sciences, well, numbers are basically just placeholders for something else as you're trying to understand how nature works. But still, you can measure nature. You can measure technology really, really precise. But then I sort of drifted away from that as well and ended up in medicine, where you're trying to sort of measure and understand the body. And the body is an incredibly complicated machine. So my idea of just measuring everything, it didn't add up. And all of a sudden, the numbers were attached to much larger variation, uncertainty. Are we measuring the right things? Can we experiment on this or can we not? What happens? And then you drift further into health, which is nursing, public health, and all of a sudden society comes in, culture comes in, and everything just tilts. And at some point, you're not sure, are you really measuring the right thing? What does this number actually mean? And now with my background from mathematics on the one side, and then pop music and popular culture on the other, creating huge communication science TV series for Discovery Channel and stuff like that. We now do research projects on the effect of science communication, and we don't know how to measure it. How do you measure success? How do you measure communication? And we've ended up having to talking to people and do qualitative studies, literature reviews, interview studies, focus group studies. So for me, numbers is basically just a part of a continuum from the hardcore math side and over to the more qualitative side where society comes in. And to me, the appeal of official statistics is that it lies somewhere in between. Parts of official statistics is really hardcore numbers. It's maths. But still, you're trying to put numbers on something way bigger than what you possibly can actually put a number on. So to me, the appeal of statistics is the fact that it is more than just numbers. And what I will do today is I will talk about 6 different aspects of numbers that makes it less clear-cut than mathematics itself. So I will now, for the next 40 minutes or so, I will tell you a few stories, 6 stories, I think, and then we'll try to get a grasp of what numbers are, when it all can go wrong, how should you go about figuring this number statistics stuff out, right? So 1, the first thing we do is that we collect data. In order to understand the world, we need information, we need data. And as statisticians, we are interested in quantitative data, numbers. So we try to collect numbers to understand how the world works. And it sounds like a really simple thing, but just collecting numbers itself can go awfully wrong if you don't know exactly what you're doing. And there's this really famous case from about 20 years ago, because in the year 2000, the British government introduced a controversial system of star ratings to improve the performance of the NHS. That's the National Health System in the UK. It's a huge, huge place. It costs gazillions of money each year to sort of have the healthcare system in Britain. And the system not working as well as it could. Are we sort of getting our money's value for what we're putting into it? Can we be more effective? Are there certain things that we can do to sort of pump up the output of the healthcare system, get more health out for each euro that we put in? So what they decided was that they wanted to sort of quantify efficiency. And they set up a relatively short list of quality indicators that could be measured. So already now I'm thinking, can you have quantitative quality measures? Does that even make sense? But they made this short list. And one of the things that they wanted to sort of increase the rapidness of response to acute incidents. So you have this what they call them, this type A phone calls, where people call in an emergency, something really, really bad, life-threatening is happening, and the hospital care system needs to respond very quickly. And their target was that every such class A phone call should be responded to within 8 minutes. And the reason why they set this 8-minute threshold was because they saw that when they looked at the numbers for the different hospitals, they could see the tendency that you see here, that a lot of calls would be replied to within 6, 7, 8 minutes, and then the whole thing would drop. And after 9, 10 minutes, it would be almost no calls. And the target was set that they wanted to increase the amount of calls that was responded to within 8 minutes, right? 75% of all calls, call A, most life-threatening type, should be responded to within 8 minutes. It's very measurable. It's a quantitative measure of quality. And all hospitals sort of rush to sort of increasing their competence here. They want it to be better. Because one of the things that the system said was that if your performance is poor, if you don't do well on these indicators, you will get a low star rating. And all hospitals who will get the 0 stars, they will be named and shamed. They will be put on list. It will be publicly available. Everyone can say, boo, you did a bad job. And they thought that this would sort of be a good incentive to sort of push hospitals into answering calls more rapidly. And when they, after a few years, they sort of looked at how this sort of push had worked, it looked good. Because in the numbers themselves, it actually looked like a lot more calls had been responded to within 8 minutes. So efficiency seemed to go up. But then, of course, the number crunchers started to look at the numbers themselves, and they found something peculiar. Because what it looked like in a lot of hospitals was it looked like this. So what had happened was basically, since the hospitals themselves were the ones who reported on how long it took to respond, when it took 8 minutes, 5 seconds, they would just manually adjust it to 7 minutes, 55 seconds. If it took 8.5 minutes, they would adjust it to 7 something. So all the data that were above 8 minutes, a lot of them would just be put to just below 8 minutes. So you have this enormous spike before it drops dramatically. This does not represent truth. These are the reported times that you can find in the Excel spreadsheets, but it's not the truth. Basically, what had happened was that no one wanted to be the ones who were named and shamed for acting poorly, not doing their job. So they created a culture in which people felt the need to sort of report the right time and started entering actually the wrong numbers into the data sets in order to sort of do the right thing. So when we collect numbers, you have to know where the numbers come from. Are they collected in the right way? Who collected the data? Why is it like this? If not, you could find stuff that's not there. And the after image here does not represent reality. It depends what happens, or actually it represents what happens when people feel bad about something and they are trying to adjust everything. So a quantitative measure of quality, I don't know. Can it be done? Check the numbers that we collect. So the second thing I wanted to talk about is data that we already have. Because we live in a world that just produces tons of data, tons of numbers. And it's kind of one of the big talks of town, right? Big data, Google, Facebook, everyone, huge data registries that we have, where you just have data. It's a great thing, isn't it? Because then we can figure stuff out. And the good thing about data registries, whether they are big or small, is that we have data. But data that we already have, they have a peculiar feature. And a lot of my colleagues, they don't talk about big data. They talk about big data as a subclass of something else, a subclass of what they call found data. It's data that's just lying there. And anyone who wants can just go in there and have a look at the data and pick parts of it out. And what happens is that people are different. So they will look at different things with different eyes. And they will, of course, find something in these found data eventually. And if you just look around for long enough, you will find something. And wait, what did you really find? Well, it depends on what the data look like, because you haven't collected the data yourself. They were just lying there. You took them and you did something to them. But the data will actually define what you can and cannot do with them. And I remember when I was a postdoc, after I did my PhD in probability theory, I did a postdoc because my pop career didn't happen, right? So I did a postdoc in medical statistics and biostatistics. So we're sitting in there in the hallway full of stats nerds working on health-related stats problems. And since we're a bunch of number geeks, we just love to do maths and statistics on the body and health and stuff like that. In order to get inputs from the outside, every second Friday, we would invite people who did research from other fields just to see what they were doing, what they were thinking, what methods they were using, what things they were focusing, what struggles and problems they had, just to sort of ease our minds into new ways of thinking. So we were sitting there every second Friday, having our lunch boxes and maybe a little bit of cake and wine lottery and things like that. And one Friday we had this guy in, and he was studying sports. He did sports research, and he was really keen on track and field, running and throwing stuff and things like that. And the good thing about track and field is the fact that it's an old sport. It's a huge sport. It's a big sport in the world. So there's tons of data. And of course, he was interested in how do you win gold in track and field? It's a big deal, right? How do you win gold? So he was going through all the data from running and jumping and throwing and various events and trying to crack what it takes to win gold. And we were sitting there, with our lunch boxes and eating our cake. And we're like, there's something here that's not right. But we couldn't put our finger on it. Before he came to height jump, I mean, how high can you jump? Where you put the bar up and you jump as high as you can. And he presented the numbers and his analysis and the results and the statistics. And then eventually one of the professors, she raised her hand because he had just said that men jump higher than women. Of course. And so the professor, she raised her hand and she was like, maybe men jump higher than women because they are taller. I mean, could it be as simple as that? So it doesn't have to do with gender or sex, sorry. But it actually has to do with body size, right? And the researcher, he was like, yeah, he'd actually been thinking about the same thing. It's just that the data didn't contain information on height. So it was impossible for him to check it. So he used sex instead. And all of a sudden, a problem that maybe had to do with body size was turning to a gender thing because that was the data he had, right? And the problem is, of course, that a lot of journalists love this idea about men are stronger than women and they run faster and they jump higher. So that story just, some journalists picked it up and ran with it. Basically just because a piece of information was actually missing in the data. And there's a problem with data that we already have. It is the fact that we are not controlling the process. In a scientific experiment, the traditional way of doing science, you have a question, and then you collect the data, and then you get an answer, you get the results. That's how a scientific experiment works. You have a question, you collect the data you need to answer that question, and you get a result. With found data, it's the opposite. You have some data. The data will define what questions you can and cannot ask. And then you get a result to that question. So what is the result again? What question are you really answering now? Are you answering the question that you wanted to ask? Or are you just answering the question that the data allowed you to ask? And there are pieces missing, which means that your whole analysis gets distorted. Body size was the important thing, but you didn't have information on it. So you turn it into a gender thing instead. Found data, registry data, they're a great resource of information, but they have some caveats that you need to be aware of. The methods we use. We have numbers. And statistics deals with having numbers, and then you pull out something essential from that huge amount of data. You're trying to find some tendencies, some patterns, because you can't just hand over all the data. You have to do something. You have to do statistics with the numbers. And the thing is that the same data, the same pool of numbers, you can do different types of statistics on them, and they will all be right, but they might still give different conclusions. So which one do you choose? And I was approached at some point by some researchers working at a hospital in Norway, because they had this huge registry, the Norwegian trauma registry, which means a trauma is when something instant happens, right? You get knocked in the head or you fall down from a ladder, something instant, your body gets a trauma. Cancer is not a trauma because it evolves over a long period of time, but being stabbed by a knife is a trauma. So we have a trauma registry in Norway, and they've been looking at everything. And then this whole thing sort of pops up. You know, people believe that during a full moon, there's more crime, and during a full moon, this and that happens. And it turns out that a lot of people think that when Mercury is in retrograde motion, bad stuff happens. And retrograde motion of Mercury basically means that Mercury is the fastest planet orbiting the sun. It goes really, really fast. And what happens then is that when Mercury sort of passes us, every now and then it will look like it moves backwards. And basically what happens if you drive past a car on the highway and you look out the window, actually when you're not thinking about the fact that you're moving, but you're just looking at the car, it looks like the car beside you moves backwards. But it basically just has to do with the relative speed of objects passing one another. And every now and then, it happens about 3 or 4 times a year, it looks like Mercury on the night sky will move backwards before it goes forward again. And there's some Babylonian superstition that says when Mercury is in retrograde motion, a lot of bad things would happen. You know, people will fall down the stairs. You won't get the job you apply for. Your boyfriend or girlfriend leaves you. There's supposedly tons of bad luck when Mercury is in retrograde motion. So the people with the Norwegian trauma registry said, well, having a trauma, that is really bad luck. And we have tons of information on trauma over a 10-year period. So let's check it out. Is it true? Are there more bad luck? Is there more trauma when Mercury is in retrograde motion or when it's not? So we took 10 years worth of trauma data, coupled it with astronomical data, and tried to see whether there was an association. If it was, well, then maybe we should do something. Maybe we should have more nurses at the hospital when Mercury is in retrograde motion. We can do something, right? Once you find an association, well, you can do something. That's good. So we collected all the data, and then we just counted, right? And the first thing we want to do, or the first obvious thing to do, is really, would you just count everything? So throughout the 10-year period, that means 3,652 days, there were about 10,000 admissions because of trauma. That means about 2.936 every single day. There was someone falling, getting a bump in their head, being stabbed, the taxi door sort of slammed in your arm, so you had to go to the hospital, something like that. 2.936 average every single day. And then we split it up into Mercury in retrograde and not in retrograde motion. And what happened is that the average for when Mercury is in retrograde is 2.992 per day. And when it's not in retrograde motion, it's 2.922 per day. So there's a difference of 0.07 per day. It might not sound as much, but when you multiply this by 745 days, that's more than 50 trauma admissions. And for those 50 people, that would actually matter. I mean, if it's a really, bad trauma, it's being stabbed by a knife, 50 persons actually matters. And it turns out if you create a confidence interval around this, it says that the true value would lie somewhere in between 0.064 and 0.075. So it means it's statistically significant. it's actually there. And we're like, huh, that's odd. Because we honestly don't believe that how Mercury sort of moves across the night sky would affect trauma admissions in Norway. So then we split it up and we started looking at individual months. I mean, we're in Norway, so we have huge seasonal differences. Tons of snow in the winter, warm in the summer, and it's raining all of autumn. And it turns out when you look at the difference in this huge table, you will see that there are pluses and minuses. It means that sometimes, for some months, there are more trauma admissions when Mercury is in retrograde motion, and for other months, it would be the other way around. And it's inconclusive because it's scattered everywhere. So what was said was that, okay, we have to do something way more advanced. So we put up an advanced statistical model. I have a PhD in probability theory, so I know how to do proper stochastic modeling. So we said, this is the amount of trauma admissions every single day for 10,000 days. And it's about, on average, as we said, about 2.9 in average. And we're like, is there an association with Mercury in retrograde motion? And you will see the gray lines here, that's the number of trauma admissions. And then the bumps, it's when Mercury is in retrograde motion. So I put up this model to try to model how this actually works. And we're trying a more and more sophisticated statistical model to try to fit the data. And the first thing we saw that in the 10-year period, there had been more trauma admissions over time. And we realized that we had to sort of compare a lot of models. Do you know the AIC? It's a way of evaluating different stochastic models on the same data. And the number itself doesn't matter, but if there's a difference of 2 or more in the AIC, then you have a better model. So just a linear long-term trend. This is an AIC of 14,729. Okay. And then we tried with a non-linear long-term trend. And the whole AIC dropped significantly. This is better. And then we added seasonal effects. And it dropped a lot more. So this is better. And then we added Mercury in retrograde motion as a covariate. And now the model is worse. So no effect of Mercury in retrograde motion. It creates a worse statistical model than when we take it out. So what does this tell us really? Well, it tells us a couple of really important things. It tells us that using a too simple statistical test, too simple statistical analysis, we would have found evidence that Mercury in retrograde motion is associated with trauma admissions in Norway. I mean, we would have backed up Babylonian superstition if we had used a too simple statistical analysis. That wouldn't be very good, would it? And then this points to a bigger thing. It says that traditional statistical approaches, just counting stuff, they are developed for experiments, right? That means the real world is just nilled out by design because we are creating an experiment. Then we can use simple statistical tests. If you don't have an experiment, but you have observational data, then the real world has to be nilled out in the statistical analysis itself. So you need a way more advanced statistical analysis when you collect real-life data instead of doing an experiment. And you can end up finding things that aren't there. So we collect data, we analyze data, and then we have some results, and then we can present those results. And there are many numbers that we can choose to represent our results. And it will matter how people are being affected by what you say. There's this famous case from 1995 in the UK. So this is the front page of the Sunday Times magazine. It says the kiss of death is the pill doom, right? It's a really aggressive front page. And it has been called one of the most deadly front pages in human history. And the reason is because there came an announcement from the UK Committee on Safety and Medicine in 1995 that said that the new generation of contraceptive pill doubles the risk of fatal blood clotting. Blood clotting is basically that your blood just clots. It's what happens when you have a wound, right? And then it would just clot and it will stop bleeding. When that happens inside your brain, well, you might die, right? And they made a statement that said that the new contraceptive pill that women put in their body, it doubles the risk of fatal blood clotting. It created, of course, fear. A lot of women, and particularly young women, they were really, really afraid. They thought they could die by taking the contraceptive pill. And the year after, more than 10,000 extra abortions happened in the UK. And we know that an abortion, I mean, it's surgery, right? You're going inside someone's body to take something out. It's a really invasive procedure medically. And 10,000 abortions, that means that there is a high-risk procedure, 10,000 more of them than usual because of this statement. But when you look at the numbers, there's something funny going on. Because the risk of fatal blood clotting is not really high. It says here, or the numbers said that the risk of blood clotting, if you don't take the pill, is 1 in 7,000. If you do take the pill, it's 2 out of 7,000. It's a doubling. That's true. But the risk is still 0.0 something percent. It's almost non-existent. But here, the choice of reporting the relative risk instead of the absolute risk resulted in 10,000 more surgical abortions. It created a way more harm than the pill itself. The numbers we choose to give out as a result of our statistical analysis matters. And then it also turns out how we present the numbers matters as well. If we present the same number, but in different ways, people will think about it differently. So there's this center in Cambridge called the Winton Center for the Public Understanding of Risk. I love their work. They're awesome. And they've done, during the pandemic, a lot of experiments with how people perceive numbers. And one of their experiments that I love the most is they asked a lot of people just how risky does this particular chance of dying of COVID-19 feel? And they just made numbers up just to be able to compare different ways of presenting the same numbers. And they said that, okay, a 5% risk of dying of COVID-19, how does that feel? And people will say generally that it didn't feel that bad. It felt low. But then they rephrased it, not as 5%, but as 5 out of 100. And that felt like a higher risk to people. It's the same number, but it feels more risky. And then they rephrased the 5 out of 100 as 1 in 20, which felt like a way higher risk. It's 3 ways of representing the exact same number, but it feels different with people. Percentages don't feel that bad. 5 out of 100 feels more, and 1 out of something feels a lot worse. And this tendency was consistent. If they said a 20% chance, well, it felt like this risky. When they rephrased it as 20 out of 100, that felt riskier. And 1 out of something, here 1 in 5, felt way riskier. So the way you present your numbers matters to people. And it turns out, when I started reading about this, it turns out that in marketing, this is a well-known trick. And it pops up in a lot of marketing blogs every now and then. And it says that if you want to tone a risk down, you use percentages. Then you tone it down for people. If you want to emphasize it and sort of push it forward in people's minds, you use the fractions 1 in something. because then people can see that in front of them. 1 in 20. I mean, you can see a group of 20 people in front of you, and you're one of them, right? So that marketing trick, just know that we too, as statisticians, representing official statistics, representing research, objective truth, know that the way that you present your numbers will actually affect how it's being perceived. And I was listening to a podcast the other day. This is actually a penis cake. The things people bake, I mean. But the thing is, I was listening to a podcast the other day. It's a stats podcast. It's called Stats and Stories, where they talk about different aspects of statistics and stories and society and things like that. And there was this professor. He was talking about reading, writing, and risk literacy. That the risk literacy is way lower than reading and writing. And in a quantified society, we should know more about risk literacy. We should know how to read numbers better. And he told this story. Well, he actually told it better than I'm going to tell it. So go and listen to the podcast. But he told this story about this German medical doctor who, as a medical doctor, you would, of course, every now and then have grown men in who have problems with blood pressure. That happens when you get older. And since the blood pressure is related to the erection in your penis, it will affect your sex life. And so we had this pill that I would often give them. And he said that 20% of the people who I give this to will have problems with their sex life. And he realized, after having done this for a while, giving out this pill saying 20% risk of a bad sex life, everyone was unhappy. Everyone was unhappy. And he was like, but 20%, I mean, that's not that bad. Why is everyone unhappy? And then he rephrased it and said, here's a pill. 1 out of 5 patients that I give this to will have problems with their sex life. And now everyone was happy, because people had interpreted the 20% thing like they personally would have problems with their sex life 20% of times they would have sex with their wives. So everyone thought they were affected by taking this pill. But when he said 1 in 5, everyone was like, 1 in 5, that's not going to be me. That's going to be someone else. And they were really happy. The way you present your numbers will affect people's lives, their feelings, their actions, and what they're going to do. And then finally, number 6, how we talk about numbers matters. I'm sorry to tell you, but facts are dead. And when I say facts are dead, I mean that facts are basically just dead information, just lying there. Facts are not alive. It's just, dead things. And dead things, we rarely have an emotional connection with dead things. And it's hard for us to sort of get all these facts into our brains. That's why we tell stories. Stories is basically the way the brain remembers. If you tell a story and you put numbers in there, it's a 20 times increase. 20 times increase that people actually remember the number if you put it into a story rather than just giving them the number itself. We who like numbers, we think that when we give people numbers, we do something good. But basically, they will forget them. 20 times more likely that they will remember the thing you tell them if you pack it into a story. That's why I've been sitting here for now 45 minutes talking about statistics by telling stories, because that is my hope, that you will remember some of the stories and by that remember the information. The body, the mind is not designed to remember facts, but it's designed to remember stories. That's why you can retell everything about your own life. You can tell when you met your now husband or wife, what happened when you lost that game, when your friend lost that first front tooth. You can tell all the stories because it clicks in your head. but you struggle to remember how many countries are there in Europe now? Honestly, I don't know. And it's weird. I live in Europe. I've been living in Europe for all my life. And with the new states, and I don't know. Stories. And I'm just gonna show you a short, play it back, a short clip. And I hope I remember to turn the sound on. If not, I'll. If I forgot to turn the sound on, you have to go to Radiolab. It's a podcast. And you find it everywhere. And you look up the antibodies part 1 CRISPR. And what they're going to do is that they're in that episode, they're talking about CRISPR. I mean, it's life science, biotechnology. It has to do with gene editing, cut and pasting, stuff like that. And it's really hardcore. It's really advanced. And I tried to understand it, and it was so advanced that I couldn't care less. And then I listened to this podcast, and this introduction to this 45-minute episode is 60 seconds. And I think it must be the most well-spent 60 seconds of jabbing along I've ever heard. Let's just cross our fingers. Maybe if I turn up the volume here, we'll see what happens.
This is Radiolab. I'm Jad Abumrad. I'm Robert Krulwich. Okay, so let me explain to you how I got started with this.
You were some kind of an affair?
Yeah, so I'll tell you how it got. I was at a party. It was a conference where they had a lot of different people of different disciplines come together. You know, one of those. There are panel discussions of various things. So we were at one of the like functions, and it was a situation where like dinner hadn't yet been served, and there was a lot of booze being served. So everybody was like drunk on an empty stomach. So I was standing there with some biologists.
Well, they're the fun ones, the drunk biologists too.
That's my people apparently, and they started to lose their shit, like genuinely lose their shit about this thing called CRISPR. And like I have never seen scientists this excited about anything. So I was like, "What is this thing? What is CRISPR?" And they were trying to explain it to me, but they couldn't slow down enough for me to get it. I gathered it had something to do with genetics, and then at one point, one of the biologists turned to me and was like, "I'll tell you what it is. I can use CRISPR to take a little dog and poof, make it into a big dog. Give me a Chihuahua, I could turn it into the size of a Great Dane." And I was like, "No, you can't." He's like, "Yes, I can. I could do it with CRISPR." I was like, "What the hell is this thing?"
Exactly. So he ends the whole thing. He's been talking back and forth, and he goes, "What the hell is this thing?" And that's what I'm thinking as well. Now I'm really, really curious. What is this CRISPR thing? And then they go on and on and on and on, talking about the details of what it is. But being able to grab people's attention, make them interested in what you want to tell them. If not, they will just move on, and your statistical analysis can be as good as ever, but people won't listen. So I've been talking about 6 things now. The data that we collect. Right? Are they good or are they bad? Is there something in the collection procedure that we have to be aware of? Then there's the data we already have, the registries. Good thing, but be aware that they decide what questions you can and cannot ask. Will that be important? Maybe, maybe not, but you have to be aware. And then the statistical analysis that we do. Simple counts may be too simple a statistical analysis, because we have observational data. We don't do experiments. It means that, we have to probably do more advanced statistical analysis than a lot of people do. Then we have to know which numbers to choose to present to people, because it matters. And then how we present the numbers, as percentages, or fractions, or whatever, it matters, right? And then we must understand that just numbers, a fact, a simple numerical fact, is very easily forgotten. If you're able to pack it into something bigger, the chances are higher that people actually remember it. I want to spend a couple of minutes just talking about the research that I'm doing now, because I've been very interested in communicating science for the last 10 years. I've been on TV and radio a lot, writing articles in the newspapers and stuff like that. And the pandemic has been a huge learning arena for us in terms of what works and what doesn't. During the pandemic, numbers, statistics has been really, really important. And this is from a press conference in Norway. And it's really funny to see that the one talking is not the Prime Minister. It's not the Minister of Health and Care Services, but it's the Director General of the Norwegian Institute of Public Health. That's the public health scientists and the statisticians. They're talking because numbers have driven how we have run our societies for the last 2 years. So then I established this huge science communication research project where we wanted to see, can we find out how we should best communicate science? And we used the pandemic as sort of a means to figure that out. And the fun thing is that just by following public communication of science and statistics for the last couple of years, there's tons of really, really good lessons to be learned. Because communicating facts related to risk phenomena, it's actually an interdisciplinary field. Because you have risk communicators, that's politics and things like that. Then you have the health communicators working with hospitals and things. And then you have the media communicators who know something about digital media and television and everything. And it turns out that they don't have the same focus. The risk communicators are concerned with trust. If you don't trust the person talking, you won't listen. So they're really keen on trust. People who do health communication, they want to give people information, health literacy, so that people can make better decisions for themselves and the people around them. So they are concerned with literacy. And then you have the media communicators who are concerned with the, the attention-grabbing stuff, because if no one clicks on the thing, if no one watches the video, it doesn't matter what you say. And within this field, we created a research project to figure out how do we talk about science. And we ended up with this thonk summary. And it says that in order to reach out with science, statistics, numbers to the general public, 5 things. It has to be trustworthy, but it can't be boring. Then people will shy away from it. It has to have human emotion. People are human beings and we make decisions based on our feelings. But if it's overly emotional, people will feel emotionally manipulated and they won't listen. Then it has to be optimistic rather than pessimistic. And the problem is we're trying to be realistic, but we the officials, we tend to be realistic, but on the negative side. People don't like all that pessimism in their lives, but the bloggers and the trendsetters and the actors who had like positive messages had way more traction during the crisis than we. So optimistic rather than pessimistic, but it has to be realistic. We can't lie, right? And then it has to tell a story, has to have a narrative. The funny thing here is that people say they love factual information better, they trust it more, and experiments show that they learn more from it. The problem is that they don't care. They will never choose to watch it. They will never share it with their friends. So you will never get any traction in the public. Right? That's a tough one. And then finally, you're in a competitive media market. Everyone's competing for everyone's attention. And it needs to be creative and stand out. Because if it doesn't stand out, people will not see it because it will just blend in with everything else. But it can't be too crazy. Because we're not selling Nikes or Coca-Cola or hamburgers. We're selling official information. So it can't be too crazy. So the thonk summary basically tells you that taking official information, getting it out to people, is a really, really fine line that you have to balance. So even though you do official statistics, your job isn't really done when you have crunched the numbers. Statistics is something way, way bigger than just looking at the numbers themselves. This is my almost final slide. Telling stories is what humans do. But they tend to tell stories about themselves. or their mother or their friend. That's what we call an anecdote. It's a story about one person. They're really powerful. People love them, but it's still just a story of one. Statistics is when you take a lot of people, a lot of individuals, a whole population, and you tell this story about this group. So statistics is also storytelling, but it's the story of the many. Anecdotes is the story about the one. Statistics is the story about the many. And that's the story that we as statisticians have to learn to tell. It's a struggle. Numbers is the first step, but if you only take the numbers in, crunch them, and give them back out, it will be really hard to make people listen, make them care, and it'll be harder to change society in the way that we maybe want to change it. Numbers are just numbers. But numbers are not the numbers themselves. Numbers represent something bigger. Numbers 37 on the screen now. I mean, if that's your body temperature, it's a really uninteresting number because everything's fine. Nothing that we have to do. But if it's your body mass index, you're heavily overweight. We need to help you with your life. Numbers are attached to something bigger. They represent something bigger. And that's what we need to be able to get out. Statistics is not the numbers. It's way bigger than that. Thank you.
Thank you. Thank you, Jo, for this very interesting presentation, and I think also for our students. So we have time, just a couple of questions that I received. So about the analysis, because I was actually also talking about, the Simpson paradox last week to my students. So the question is, since some students just study learning statistics, so they ask, so when we should stop? I mean, to be sure that you are actually analyzing the data in the correct way, should at least try to use a model instead of a simple cross tabulation. So that's the question. Because you use very advanced modeling. So
now it's a really, really tough answer. And to me, that is one of the beauties of statistics, right? Mathematics is black and white. It's right or wrong. That's it. Statistics deals with shades of gray. That's the universe that we're sort of moving around in. And we don't have the answer to what is the right and what's the wrong analysis. You have analysis that would probably be better than others. You have someone that may be too advanced, someone may be too easy. So that's why when I've been involved in, hundreds of research projects, literally, and we spend a lot of time discussing that. Do we have to make it more advanced? Or can we stick with a simple one? The simpler analysis, the better. It's easier to do. It's easier to understand, right? It's easier to sort of tell people about. And the really advanced model, you risk of over analyzing the whole thing, right? But I don't have the exact answer. That's why we as statisticians, we need to talk to one another. We need to talk to the experts from that field that we are analyzing the data from. I mean, when I analyze surgical data from a hospital, I talk to surgeons. When I study communication data from public health, I talk to communication experts and public health experts. When I do maths on health economy data, I talk to economists. Does it seem right? So it's a huge paradox. It's really, really hard. And I don't have the answer. But what I usually do is I do very many different statistical analysis on the same amount of data. If I get the same answer, perfect. Then we're good, right? And that happens a lot of times. It doesn't really matter how you approach it. It will be the same answer. But when there are differences, which one do I choose? Yeah, and I have ended up publishing the wrong one. I have. And 5 years later on, I realized that, that must have been wrong. Can't be right. Feels really horrible. And then you get a couple of nights where you can't sleep. But then you realize that it's going to happen. It's statistics. It's uncertainty. It's probability.
Yeah.
I know it's not the answer you wanted, but it's
No,
that's, but the same is great. That's where we live, right?
We will ask the students. And then another question is about when you present the numbers. So it also makes a difference if you use some graphical representation instead of just a table. And if you have any suggestion about that, the difference.
Yeah. Sorry, go ahead.
Yeah, please. I mean, what is the difference in your opinion or in your experience to communicate using just a table with numbers or a graphical representation, if this makes a different impact in the readers?
Yeah, I will answer that in a very popular science, popularized way. If you want to be famous, do you go on television or do you write a book? You go on television, because people are visual beings. We like to watch things. 80% of all the information we take in is through our eyes, and from before we can read and write, we make drawings of the world around us, and we understand what drawings and visual representations mean. Visual representations are incredibly strong. You will remember them way more than just the simple numbers and tables. We who are the trained scientific professionals, we understand tables. This is our language, but we are a minority in the world. Most people prefer graphical presentations, images. And why on earth do you think I presented a penis cake? Because, I mean, I can talk about a penis cake and people smile and laugh, and you will remember the story with the penis cake and the doctor and the erection problems, and hopefully that will make you remember something about the numbers. Had I just said 1 in 5 versus 20% with no graphical information, you would probably have forgotten. So the answer is, if you're talking to scientists, tables and numbers are just fine. If you want to reach out beyond the inner congregation of stats geeks, but to the general public, decision makers, anyone, use graphical representations. Spend a lot of time on finding good representations. Sometimes it's a great table. Sometimes it's a great graph. Sometimes it's a great chart. And sometimes it's just an image, right? I spent huge amounts of time finding the right thing. I mean, just look at the front page here, right? So you have on the one side, there's equations and a girl. And on the right-hand side, there's a market. And my hope is that you will remember that it has something to do with maths, and it has something to do with people out in the real world. Right? And I was thinking, I was sitting up late last night, and I was like, should I put the girl in front of those equations, or should I let it be just the equations? And I was going back and forth and back and forth. What would be more powerful? And I'm not sure if I made the right choice. My choice was I choose the equations with a girl because maybe the girl will resonate with a younger audience and they will see themselves in the girl. But on the other hand, it would be a bigger contrast if it was just the equations and then people in the real world. You have to dare to spend a lot of time and think about it. A good visual representation gets your message across way more efficiently than just tables and numbers.
Okay, yeah. Thank you, Jo. I think the time now we need to close. It's finished. So thank you, Jo. Thank you again for this very interesting presentation, and many thanks also to our participants. So the recording of the webinar will be available on this YouTube channel, where actually you can also find the recording of the last EMOS workshop, and Jo was also a presenter at the last EMOS workshop. And then for the webinar, you will shortly receive to the email address that you use for registering to the webinar the link to a short survey about today's webinar. And we'd really appreciate your feedback to further improve our webinars. So for the moment, we have no EMOS webinars scheduled in the future, but I think that some new webinars will be organized and you will be informed about that. So thank you, Jo, again, and have a nice evening to everybody. Bye.
Bye.